So good afternoon, everyone. And I'm going to continue slightly on what the background Eric already has laid down. But I'll take you more into the area of hardcore electronics and what we call as the printed electronics. And also a bit on the flavor of my talk will be a bit on the material side, because I deal with a lot of materials. And the idea is to make this whole industry sustainable and how we can do that and what we as a research group are doing. But before I dwell into that area of my research and my research group, I would give you an overview of what printed electronics is and what are the different equipments and technologies and techniques that we are using in this area. So just a snapshot of where I come from. I come from Aarhus University in Denmark. It's the second largest and the oldest research university. And we have a huge department of engineering, and I belong to the Department of Electrical and Computer Engineering, where we do all sorts of things. And my core area basically lies within electronics and photonics, where we are doing printed electronics. Now, the flavor of my talk, as I said, would be introducing you all to what printed electronics is. And I'm pretty sure a lot of you already are aware about it. And then I'll go a bit deeper into the drop-on-demand technologies, which we use, especially for printed and flexible electronics. And then I'll take you through the route of my own research group, what we are doing at Aarhus universities, and finally closing it with the potential applications. So we all know how we want our electronics to be for the future. It needs to be flexible, bendable, stretchable, conformal, lightweight, and all the aspects that we want. And that's the vision of electronics moving forward. And some of that you have already seen in a few of the talks earlier. How do you do that? Well, if you want to make something more flexible, bendable, stretchable, the first thing that comes to your mind is when we have a huge silicon industry. And when you look at the processing, you would find that two key components which are kind of hindering blocks to that. One is the high temperature and the other being the high vacuum conditions. And most of the new materials that you deal with, that you want to print, they're not compatible with them. And that's where you have to come up with new ideas or new ways of putting electronics or making or manufacturing electronics, which has not been done. A bit of that was already covered by Eric before, where he has shown different technologies, mostly related to polymer and metal printing. These technologies that I will talk about are mostly catered for only electronics. The idea of is putting electronics where it may or may not belong. Why can't I print electronics on the speed of wood that you're sitting on, or a plastic bottle, for example, or as Eric said, on a packaging, for example. The whole range of potential applications is wide. And unfortunately, when you look at the new applications where we say that electronics is flexible, let's say these Fitbit bands, the wearable bands. If you closely inspect them, they are bendable, but they are really not flexible. They're not flexible like a textile. They're not flexible like any plastic that you can stretch and do. So the idea is to basically stretch those boundaries of electronics and take it further and make something which is even more bendable. So what you do in this is basically take a pattern, just like in any 3D printing. You have a digital design, then you have a printer, which is associated with that printing design, compatible with it, and then you have a substrate. And in this case, the substrate of your choice could be anything. It could be wood, paper, plastic, biomaterials even, and I will show you some examples moving forward, where we have tried to print electronics with biomaterials, tissues, and cells even. Because we want to basically see the potential of electronics, which can be expanded from traditional applications. So, as I say, this is basically the start of, I don't like the music for the page. Okay, so then, and then you have a printing. So the desktop or the printer is very close. You have already seen Inkjet printer, which is sitting in offices and homes, where you have computer command that you give on your word and you want to print something, and the command goes to the printer and well, in a very beautiful way, where what we do is simply replace the black and white and the color inks from printers with what we call as functional inks. The functionality of the electronics that you want to print comes from these functional inks, in the sense that I can have conducting inks, I can have semiconducting inks, I can have insulating inks, and then I print them as per the design of my design file, and then I put it on get the command printer, and then I have a substrate ready to be printed on. And again, as I said, we, as you will see moving forward, we have experimented with a lot of substrates. It could be paper, it could be plastic, it could be textiles, biomaterials, cells and tissues. And that's the beauty. When you look at the whole area of electronic printing, there are basically two main categories. One we call as contact printing, which basically the name suggests is that the print head is in contact with the substrate. So it's a close contact proximity printing. And it has pros and cons. The drawback being that sometimes you damage the substrate that you want to print on, and that leads to other problems as well. You have scratches, you have discontinuities, but screen printing, I would say, is the most successful, near to commercialization printing of electronics process that is out there right now. It's not per se commercialized, but as is being put together with other printing technologies and other traditional technologies to be taken to the market. So it's much more closer to commercialization than any other printing technique that I will talk about so far. Then moving away from contact printing is what we call as non-contact or direct write printing. So the whole idea is to simply print electronics just the way I pick up a pen and write on a piece of paper. So if I can draw on a piece of paper with a pen, then I should be able to write exactly the same way. And the way two main technologies dominating this area are, what is one, as I just showed, is inkjet printing, very close to your desktop printers in your homes. And the other is, which also Eric mentioned, is aerosol jet printing, which I will tell you what is the main difference between the two. So in inkjet printing, you can do 2D surfaces, but the beauty of aerosol jet is you can print on all 3D curved bendable surfaces that you have. And it comes from the fact because the printhead, you can basically play with the distance between the printhead and the substrate, which is so not possible with the inkjet printing. And when I talk about printed electronics, well, people who don't know or who don't come from this area, a lot of you already are aware of this, is they say, oh, it feels pretty easy. You know, you have a bottle of ink, you have a printer, your life is easy. No, it's not. Trust me. One small change, and then you have to go through the whole mesh of optimization all the way again. And there are some pretty common problems that we deal with in printed electronics. Sometimes what you want is basically what I call as a good printable quality, which is a good line quality. It should be homogeneous, crack-free, should adhere to your design parameters. So if I design a 10 micron line, it should end up as a 10 micron line. But that's not the reality. Life of a researcher is hard. You all know that. So what you end up is bulging lines. You know, you have too much of ink coming out, or you have discontinuous line where you don't have anything coming out of the printer. And it happens because the inks that you are using, the particles that you are using in the ink, basically are not compatible with the print heads, the openings of the print heads. Sometimes if it's too big, nothing will come out. So when it comes to printed electronics, the heart of getting a good print quality lies with the printed inks. Your printed inks have to be really compatible in viscosity, in rheological properties, in the particle parameters with the print head that you're trying to use. And this is how it looks like. So this is a simple strain gauge design on a Kapton. And if I were to zoom in and magnify, these are how the lines, a good print line looks like. And if I zoom in further, basically it is nothing but a mesh of nanoparticles. This is basically silver. So this is silver nanoparticle ink, which is basically a cloud of agglomerated silver nanoparticle, which causes the electrons to go in a more continuous path. Now, although this technology is fairly new, this landscape has been emerging, I would say, last decade or so, but it has grown leaps and bounds in the last decade, where a lot of people have basically come into this area and tried to not just increase the resolution of the printing, but try to experiment with different materials that we can print. Because you will see moving forward that we are limited. When you pick up a printing technique, you have to think about what resolution you want to print, what is the material you are printing on, and what are the applications that you want to print for. Because in certain applications, you need certain resolution, in certain, you need certain bendability, stretchability, which is not possible with other applications. So you have drop on demand based direct writing techniques, which I will talk about and go into detail. Then you have energy-based techniques where you use some kind of energy, whether it's laser, whether it's electron beam, to basically melt the material or your inks or whatever particles and directly deposit them and cause the circuit or the continuous slides. Then you have the flow systems, which are based on fluid mechanics, and different kind of flow systems are possible through pump extrusion, where you just extrude out the material or the liquids, and then you directly write on these substrates. And then there are basically tip-based or pen-based techniques out there as well, where one of them is nano fountain probe, deep pen lithography, where you use them as a tip, very fine tips, and then you eject the liquids in different forms, and then you get different kind of writing resolutions onto the substrate. So what I will take you forward before I dwell into my own research is into these three printing techniques, which are basically what are the forerunners in the form of printed electronics. And each of them is important or player in their own right because of the resolutions that they can achieve and because of the substrates that you can print on. For example, inkjet printing is now possible to achieve around 20 to 25 micron printed line if you optimize everything with the standard silver nanoparticle ink. If you want to go further down, aerosol jet simply can give you around 10 micron of resolution right now. But the beauty of aerosol jet is that you can have it on, or you can print electronics on 3D surfaces, golf ball, lenses, any curved surfaces, curved sides of the chair or a mobile case, for example, if you want to do. Optomac has already shown these applications where they printed around the casing of the mobile phone, they printed the antenna. So you don't have to embed it, so and so forth. If you want to go further down, then you have electrohydrodynamic Inject, what we call. Basically, it can give you up to 1 micron line resolution in that sense. But as I said, these are fairly new techniques, and these are non-contact based techniques, so they have their own merits. But the biggest player in the market still remains the screen printing, which I have not covered here. So after screen printing, the most important player is Inkjet Technology, and Inject is an old technology, it's not new technology. But Inkjet Technology being used for electronics is fairly new. We started using it way back, as we have seen for metals, and also for polymers, and then we have been using digital printing for as far as I remember. But for electronics, it's been taken up the market fairly recently. And the idea here is basically ejecting material or functional inks drop by drop. So that's why it's called drop on demand or droplet based techniques, where you make the droplets and then you cause these droplets to stick together, impact on the substrate, and then stick together to form a continuous flow, a continuous path. Now, within this inkjet printing, we have two categories. One is called a continuous inkjet printing, and as the name suggests, basically what you have is continuous flow of inks. So the inks keep flowing from the printhead, and then you keep collecting it onto the substrate, and that forms a continuous flow. The other is drop on demand. Basically, what happens is that you have a mechanism where the printhead is not always open. It will only open on your demand, wherever you want or whenever you want. And that basically is activated by two mechanisms right now. One is heat, the other being piezoelectricity. So you have a printhead which can open and close depending on the heat activation or the piezoelectric activity of the printhead. And that's how you basically get these drops onto the substrate. And then once you have these substrates, so what happens is that you have an ink, you eject that ink from whatever mechanism, these droplets will sit on your substrate, And then these are liquids, right? But you need a solid circuit to be formed on your substrate. So what you need to do is first you need to let these droplets evaporate so that all the solvent evaporates. A lot of these functional inks that I'm talking about, they are not just silver particles dispersed in a solvent. It normally is not that, because the dispersion of these nanoparticles is not very good. So you have to add a lot of additives, which are organic materials, or you might have to add a lot of binders, which are again organic materials. And when you are printing, your droplet will have all these materials. So it will have the solvent, it will have your metal, for example, let's say silver nanoparticles, then it will have all these binders and additives. But you want only pure metal to be deposited, right? For your conductivities, for less resistivity, low impedance. So what you need to do is you need to evaporate, and then you need to do what we call as post-processing. This post-processing comes in the form, the most standard way of doing is heat sintering, right? You just put everything in the oven, and depending on your, again, functional inks, you can start heat treating from, let's say, as low as 70 to 80 degrees. I will show you some examples where you don't need any heat treatment as well. We have made some inks like that, all the way from, let's say, standard 200 to 250 degrees for half an hour to 1 hour. That's a standard sintering process. Once that sintering is done, the solvent is evaporated, all the organics are degraded, and then what you end up, or at least should end up, is with a pure metal or material ink that you are supposed to write. So, if I talk about continuous inkjet printing, the idea comes from, or the way it works is based on what we call as the Plateau-Rayleigh instability. So if you ever seen that if you are closing and opening, especially when you're closing your tap water, tap in your homes, there's always a big flow of liquid, and then it starts to collimate into smaller streams, and then you will have droplets, and finally the water will stop, right? Have you ever wondered why it happens? Why doesn't your water stop immediately? Why does it break down into these drops and have these things? It's basically because of this physical phenomena, which is Rayleigh instability. What basically it means is that when you have a big stream of any liquid flowing down, it is quite unstable because of its weight and under the force of gravity. So it needs to break down into smaller droplets and take spherical shapes so that it stabilizes and has the least energy, which is favored by nature. So what happens is that this is a natural phenomenon that if you have any big stream of any liquid, and it's not just for water, for any liquid, it will tend to stabilize itself by segregating into smaller and smaller droplets. And if you observe them under microscope, you will see that all these droplets, again, that comes from the rheological properties of the material. If it's water, it would be different. If it's oil, it would be different. You would have a certain shape, mostly spherical shape of these liquids, which will be breaking this whole stream into. And then this is the spherical, basically droplet, which will impact your substrate here, lying somewhere, and deposit. And then you move your printhead on the X or the Y direction, and another drop is deposited, and then you move forward. So this is how drop by drop by drop, you are going to form all your continuous part of inks. And again, if you were to look in a very realistic way, a theoretical way, then one scan or one movement of a printhead from X to Y direction should be enough, right? I have a few deposited drops in a continuous line, and that should be good enough. In reality, these drops are so small, and they even coalesce together, shrink in size after sintering, that one print pass, especially in inkjet printing, is not enough. When I'm talking about the strain gauge that I just showed you previously, I would say roughly 15 to 20 print passes are required in order to get a substantial amount of resolution, line width, and homogeneity in order to get a circuit working. If you think that your life would be easier, you're done after doing it, no, it won't work like that, because you will have, what would be the problem? The problem would be there will be a lot of cracks, discontinuities, gaps within these droplets, which will cause the circuit electrons not to flow. So you need to have different print passes. So basically, this is the idea of having a continuous inkjet process where you leave the printhead open, and the whole liquid starts to come out or eject out. And while ejecting out, it separates into these spherical droplets and impacts the surface. Now, this is not a very efficient process, and sometimes you need to have places where you don't want the drops to be. So if it's good, it's good if I were to, let's say, make a thick square of 2 by 2, 1 by 1 cm, because I need the liquid or I need the material everywhere. That's fine. But if I'm going to make a selective circuit where I somewhere want the ink to be deposited, somewhere I don't want, then what makes my life easier is what we have a second generation of inkjet printers, which is now the most used. I don't think so anybody uses continuous inkjet printing anymore. So the most commonly used is drop on demand. So as the name suggests, as I said earlier, is the ejection of the liquid is going to happen, or the ink is going to happen only when you want it to be there. And the way it is done is through 2 actuations. One is by thermal actuation. So your print head might be made up of the material which is heat sensitive. So imagine if you're raising the temperature, will open your print head, your material is going to be a function, ink is going to be ejected, and then you're going to cool the material and the print head is going to close. So this is how you're going to decide. But that is also the kind of first generation of print heads. The latest generation of print heads, I think all over, they use what we call as piezoelectric actuators. Piezoelectric is a material which converts electrical energy into mechanical energy and vice versa. So what happens is that you apply a voltage to the piezoelectric head, and that voltage gets converted into the mechanical movement of the print head. So the print head opens, you remove the voltage, the print head closes. So this is how you operate the opening and the closing of the print head. And most of the printers are now fitted with these piezoelectric actuators to give you on-demand printing of the functional inks. Now, as I said earlier, the heart of any printing process is defined by the fact that it has to have the right property of the functional ink. If your ink is not right, trust me, nothing will work no matter how great your printer is. So both have to be compatible. And again, the rheological properties of the inks are very important. It should be very well dispersed solution. Your ink should not settle down. I make the ink solution and after 2 minutes, everything settled down. No, that's not going to work, because the moment you want to print it, after 1 hour, everything would have agglomerated, precipitated, and nothing is going to come out. The viscosity of your material, whether it's low viscous, high viscous, should be compatible with your print head. If you have a very small opening of the print head and your material is highly viscous, and if you're not applying enough pressure, you will not be able to extrude out. As against the opposite, if you have a too big opening of a print head, and then your material is low viscous, then you would have too much of material coming out and you will not be able to control it. So it's always a balance that you have to find between different parameters. Otherwise, you would have all these problems like stashing, satellite drops, or coffee ring effect. Coffee ring effect is, I would say, the biggest headache for people like us. And it's very common, like if you have, I have my coffee cup here. If I leave it, if it had something here, if I leave it on the table, you would have a ring formed at the table at the end of the after some time. Why does it happen? Why do you think this coffee ring is made? How does it happen?
The liquid moves to the edge as it dries.
Yeah, so
it
it's
brings the particles with it.
Exactly. So it's basically the rate of evaporation of the material. So whenever you have any residue at the base of the cup, you leave the cup on the table, the material will start, because it's liquid, so it's going to start evaporating, right? And depending on the rate of evaporation, you would have segregation of the materials, because if the evaporation is too sudden, you would have the small particles being pushed to the side. It's basically a force that comes into play. And all the particles will basically segregate and agglomerate at the edges as against in the middle. And you have this kind of a ring effect being formed. And this is a common problem because, again, as I said, these droplets that you are printing, they need to impact the surface and you need to evaporate this solvent. And normally we are printing in room temperatures. Now, depending on your room temperature, whether you are in Denmark or in Singapore, your temperature is going to be different. And when this temperature is different, evaporation rates might be different. But it's not too much of a difference, but there is going to be a difference if you don't provide the right environment. And you would end up forming these kind of coffin effects if you are printing patterns onto your substrate. That means everything is being pushed to the side. So what you will get is, instead of having a very homogeneous line, you will only have particles of silver on the edges, but nothing in the middle. So that would create a problem because you don't have a continuous line in that sense. But there are ways now. A lot of research has been put, and I think it's a fairly solvable problem if you have the right combination of the inks and the printers. It can be easily solved. Now, that was all about inkjet printing. So as I said, inkjet printing is great, but it has two major limitations. One, when it comes to electronic inks that you can print, you are only limited in viscosity range. And the viscosity range is somewhere between, I would say, 10 to 50 CPS in terms of viscosity. Now, if you want to print materials which are outside this range, you basically have to find another way. The other problem is that most of the times when we are inkjet printing, we are only taking flat surfaces, always 2D surfaces to print on. So if you have to print on a 3D surface or three-dimensional surface, then you always have a problem. And that's where I think the aerosol jet, which is from Optomec, came into picture. What they did was they can now fairly change the distance between your printhead and your substrate. And the idea here was that anything that can be made into an aerosol, which is a droplet based droplet of the formation of the droplets in a material. So if you can aerosol, make an aerosol of the material, you can basically print it in that printing technique. The way it functions is that you take your material and then you form aerosol droplets of this material. And this is carried, so you transport this material in a system where basically all these droplets, the cloud that you are forming now, is basically collimated into a stream. Then it is further pointed into a precision direction using another system so that it passes through a very fine nozzle and then it impacts to your surface. So you see basically it's nothing but a cloud of nanoparticles in a droplet formation, which is basically being carried from the tank all the way to your printhead. And when you do that, basically you can play with a range of viscosities because anything, as I said, can be aerosol, what is the word, aerosologized or made into aerosol, can be worked with these techniques, which is not possible with inkjet printing. And because of this distance that you can vary between the printhead and the substrate, you can now have 3D surfaces here. So if I were to rotate my surface and alongside, whether you are rotating your printhead or you're rotating your substrate, basically you can have that aerosol being impacted on all the surface or all the sides of your material, of the object, rather than just having it on a flat surface. And that is the reason why you can now print on 3D surfaces. So this is some examples from Optomec. What they have printed is basically they have shown printing on these. So this is fairly achievable with inkjet printing. Of course, you would be limited in resolution when it comes to printing tags or antennas. But the beauty of aerosol jet comes from the fact that now you can print on 3D surfaces like this dome, the cone shaped, or this dome, and this lens kind of a dome system here. And they have now, I think, Optomec have shown applications in printing on lenses now, where they're trying to directly print some electronics on the lens systems for some biomedical or glaucoma, if I remember. Now, electrohydro e-jet printing, as we said, is another variation. It's not very commonly used, or it's not being popularized as screen printing or inkjet printing and aerosol jet printing, but you can really go down in resolution. The idea here is basically the same, that you use electric field now to create your inks. So what happens is that you have to use polarized material. So that's the only limitation of this kind of technique. So once you have electric field being subjected to that ink, the dipoles and dipoles in the ink will get polarized. And due to that polarization, you would have, depending on whether you apply, what kind of electric field you apply, you can have really, really fine beams being formed, which will then impact your substrate here. And then you can directly write, and you can go up to 1 micron or so in this particular technique. But because of the limited number of materials that you can print with this technique, this has not been really very popular out there. So basically, this should give you an idea of what printed electronic entails and how we can create printed electronics. And now moving forward, I will just take you through the snapshot of some of the work that we are doing at Aarhus University in our group, and what we are doing. So that's my small and humble research group out there. My research is very multidisciplinary. As you can see that when you talk about or when you envision printed electronics, there's so many scenarios that might come into your mind. What you can do with it. You can create not just consumer electronics, which is flexible and bendable, but you can take it further to biomedical space. You can do aerospace, where we have done some applications. But so what I do is hardcore electronic engineering and designing. Of course, using the 3D printing manufacturing method of printed electronics. But I do a lot of material science, and I will tell you the reason why. And most of my applications are catered towards healthcare, because I find that for printed electronics, healthcare forms a very niche area where we can really, really contribute with the kind of research that we are doing. So in my research group, we have 2 parallel paths. One is, of course, printed electronics, and the idea is putting electronics on unconventional surfaces, because everyone knows the kind of surfaces which are already used in electronic industry: glass, ITO, FR4. That's fine. We can print with traditional methods. We can do that. But if you have to push the boundaries for next generation electronic devices, you need to think, where else can you put your electronics where it doesn't belong? Can I, as I said, can I put it on a piece of wood? Can I put it with biomaterials, with cells and tissues? Can I put it with paper? So and so forth. And this is where we are pushing boundaries, where we are trying to put electronics and then trying to understand the ink substrate interaction, especially at that interface. What happens when I put a new material in contact with a new substrate? The other, which is my own passion project, is something where I'm very passionate about, is trying to marry biology with electronics. So bioelectronic devices are not new. We all have pacemakers. We have all dealt with different kind of hearing aids in healthcare, and that's fine. But they still use hard, rigid electronics, and that's not nice, because the longer that stays in your body, the more problems that will create. And the idea for next generation bioelectronic devices is to go completely flexible, or find materials and devices which have Young's modulus very close to that of cells and tissues. And that's what we are trying to do in our research. So a big chunk of my research is on material, and I will tell you why. I tried to focus on material innovation. And of course, we are doing printing processes and optimization, and trying to make it optimized. And as I said, especially study the ink substrate interactions. And then we have a whole range of biomedical and healthcare applications that we are looking at. Now, before I take you into the roadmap, I just want to make you understand why I am doing what I'm doing right now. So it all started with the fact that when I was doing my postdoc, I was expecting my first child, my only child, and I was working with perovskite-based solar cells at that time, which were using lead. And when I told my supervisor that time that I'm expecting and I cannot, so the first thing my supervisor said, okay, you need to stop working with lead right now. It's not healthy. And my doctor also said it's no correlation, but it's better if you don't work with lead. And that was the point where I really sat down and thought that if I can't work with a material that I'm using in electronics, which is going to be deployed outside in an environment, in a harsh environment, I cannot work it with me in the lab. How can I expect that material to go out and serve people if it's harmful? For example, lead. Of course, it's in a very small quantity, and I'm not trying to say that perovskite is bad. I mean, we have great efficiencies, and that's fine. People are looking in ways. But we have to think about sustainability. We have to think about safer materials to work with. And that's where basically a whole diversion of my own research happened, where I thought I need to work with materials which are safer, which are more sustainable and greener for the environment, but of course, electronically functional, because you can't live without electronics. And so we all know that electronics is the pillar of our modern society. We need it no matter what you do. Whether you are finding solutions for climate change, whether you are finding solutions for smart manufacturing, you need electronics there. But if electronics is not sustainable and safe, you cannot have a future for that electronics. And that's a growing problem. E-waste, electronic waste is a huge problem, just like the plastic waste that we are dealing with. The problem is even worse because as against or unlike plastic, where we know the numbers, how much plastic we are generating and consuming, a lot of countries are not keeping track of the electronic waste that we are generating. And imagine yourself how much we would be generating. The cell phones that you are using are made to design to work for at least 5 to 7 years. But we change them in a jiffy. We change them, next iPhone is released, you go to the market and you change your phone. You change anything, your laptop, something happens, instead of repairing, you just go and buy a new laptop, right? So how much electronic waste you are generating? And that's a growing problem. And it's not just a problem because we are creating volume on Earth, but the materials we use in some of the electronic components, they're really harmful. They're unsustainable. And when you leave them just like that without proper processing, they release toxins in the environment. And there have been growing cases of where you have these dumps that they are having, the kids and the elderly have started to have health problems. The other, as I said earlier, is that the new age of bioelectronics. We have a lot of electronic devices that we deal in biomedical industry, from pumps to stimulators to implants. But in the long run, it's a growing problem because I work very closely with the doctors. The longer the period it is inside the human body, the more incompatible it becomes. You have problems like infection, bleeding, cardiac perforation, and so forth. So they want to see devices moving forward which are more in tune with the human body. And this is where basically my vision of my research is. I'm trying to reshape the electronics where we can say that the electronic materials that we are working are not just biodegradable and green, but they are flexible and biocompatible, completely free of wires, as one of the cases that Eric also showed, and soft. So we are trying to take cues from the nature to develop new electronic materials which are greener and safer for the environment. Of course, I'm not saying that this is going to replace the market that we have tomorrow. It's not going to happen. But this could be a complement to what we already have as a well-established technology. So what we are doing is we are dealing with the biodegradable materials. This is, I think the first report came from John Rogers from Northwestern University, where he showed that there are materials available that can basically completely degrade in different environments. In this case, it was water, and leave no footprints behind. Similarly, there are a lot of medical companies now working on bioresorbable materials, basically the materials which go inside your human body, and then they electronically perform for a certain time. But after that, once their job is done, they are going to be reabsorbed within the human body without leaving any toxins, materials, or without having the need to do a second operation to extract them back. Right? So when you talk about material innovation, there are great, fantastic material scientists out there who are doing that job. And I'm not saying I'm one of them. But the thing is that what I find very peculiar I find a bridge that's not there between science and engineering. So there are people who are doing very great materials, but they're sitting in the lab. They don't see the light of the day. They never see the commercialization aspects. And this is where I want to, at least my approach to my own research is different. That I want to make great materials, but I want to make them with processes that can be scaled up and eventually be used in the manufacturing scenario in real life. It can be integrated in the workflow. And that's why I think I have looked into printed electronics and used it as a route, because printed electronics can easily be integrated in the workflow of the existing silicon technologies. It's totally possible. To work with these materials. So, so what we do in our current lab is basically we started doing with very passive devices with pH sensors, temperature sensors, strain, pressure, all those things. And then we are now starting to slowly move towards the active components of electronics, like antennas and transistors, and even multifunctional devices, some of which I will show you later on different substrates. So, but before I dwell into the case studies of the applications, I want to just give you the snapshot of what materials we are dealing with and how we are making. So the biggest problem in printed electronics is the material scarcity. If you go out to the market right now and want to purchase a material which can be printed with any of these Jet or aerosol jet or inkjet, you will see there are only one material per se which is available, which is silver nanoparticles, dispersed in either alcohol or in DI water aqueous solution. Maybe you will find some manufacturers dealing with carbon nanotubes, maybe, or PEDOT-PSS, which is the organic material. But other than that, there's no other material. Now, if the vision is to completely replace your existing circuitry, then I just cannot do with one material. Plus, silver is super expensive to work with. So we need to develop a new material library, which is not just green, but also low cost, and also has other functionalities. So 2 of my PhD students are now working on piezoelectric materials because for different kind of sensing and different kind of sensing applications, but especially for biomedical, where you need very small, very high sensitivities, piezoelectric materials really are needed. So we started with PVDF, which is a polymer. PVDF is already known for its piezoelectric properties, so nothing new here. But the problem is that PVDF's piezoelectric properties are very inferior to, for example, PZT, which is the inorganic counterpart. And the idea here was to increase its piezoelectric properties, and not just increase them, but make it printable dispersion. So we wanted to print this material. There's no commercially available material piezoelectric material that can be printed right now. So what we did was we set out by using the strategy of using fillers in our PVDF material. And in this case, we chose barium titanate. The idea was to use the positive coefficient of barium titanate and infuse it with PVDF. And then we basically increase the crystallinity of the material. Because in piezoelectric materials, especially the piezoelectric polymers, everything is crystal structure based. You change their crystal structure by a small bit, and their properties will change a lot, right? So their morphology, their size, their crystal dimensions, everything dictates their piezoelectric properties. So when you infuse barium titanate particles into them, you basically hamper their crystal structure, and then you increase the crystallinity by a few percentage. And then what we did was basically convert it into a very successful dispersion, and then used inkjet printing to print this material into making a pressure sensor. But what we found was that yes, it does increase by increasing the crystallinity, by adding barium titanate. We could increase the crystallinity of the material, but not so much. Still didn't stand a chance to make a very sensitive pressure sensor for a biomedical device. The idea in this case is basically we want to pick up the pressure from organs. Because a lot of doctors say is that if you can measure the pressure on different organs of the human body, then it can give you an indication of the diseases that you are dealing with. So if the pressure is too high on a certain organ, you know where the problem is coming from. So idea here is to get really, really sensitive pressure sensors. Now, what we did in that case was we then went to 2D-dimensional materials. So again, it might be a little out of the comfort zone for some of you. But what we did was use the polymer material because it's completely green or sustainable in that sense. It's very low cost material. And then we functionalized it with 2D graphene. And then we found was that because of this 2D graphene, it's a two-dimensional structure in a 3D matrix. Basically, it forms microcapacitors within the material itself. And because of the interaction of AGO with PVDF, we were able to get really great, outstanding piezoelectric properties from this PVDF. So we increased the properties by a tremendous amount, as you can see. For any range of frequencies, you get really high permittivity values. Even your breakdown strength increases quite a lot for certain combinations. So the idea here was to use the different kind of strategies. In another of the projects, again, we are targeting the material, which is also a piezoelectric material. when we were working with PVDF, because I work with doctors, and one problem that we have to deal with PVDF is that it needs polling. Polling is a process where basically you have to align the dipoles of the material. You have to put it inside a big electric field environment, put the material there, and then all the dipoles are permanently aligned. And then it's a good to go material. But this electric field is really, really high. And sometimes it's not really possible to put every material that you are printing and every device that you are printing, putting into the polling environment. So we wanted to look at a material which did not require any polling. And then we did our own study. And then we found that there is a naturally occurring PLLA material, which has a very, very weak piezoelectric signal. It's very weak. But the idea was to pick this up because it's completely biodegradable. It does not require any polling, and then transform and try to enhance its piezoelectric properties. And this is exactly what we are doing right now. And the way we are doing is by compression molding. So we are trying to use heat and pressure, no chemical formula here, and trying to use compression molding to change the architecture of this PLLA. And we have shown that by changing the architecture, just by this compression molding, we are able to create or increase the piezoelectric response of this particular material. So again, this is unpublished results that we have still investigating how and why, but we have some fantastic results here. And again, the moment you mold it, it's good to go. You don't have to do any molding to get a pressure out of to get a sensing property out of it. In another of the aspects, one of my postdocs, she is looking at biodegradable material, which is PDA. So what she's trying to do is she's trying to use the sticky properties that is found in muscles. Basically, when you have muscles, it has a very extraordinary property that it can stick to any surface known, whether it's organic, inorganic, wet or not. And again, this is not a new study. A lot of people has basically what they have done is try to replicate the protein which is excreted by muscles. It resembles what we call as polydopamine. And people have tried to then create this polydopamine and make a lot of sticky surfaces. So you will see a lot of self-healing, self-sticking surfaces, self-cleaning surfaces based on polydopamine. But our idea was to create a substrate which was sticky, and we didn't want to use polydopamine because polydopamine had its own problems when it comes to dispersion if I were to make it into an ink. The good counterpart or the way of solving this is instead of using the polymerized version of polydopamine, I just use unpolymerized dopamine. The idea was, it makes alive difficult because it's very difficult to keep dopamine stabilized. It always have in nature a property to polymerize itself and convert itself into polydopamine. Just give it a little bit of oxygen, the right pH, and it will convert. So it's highly unstable. But dopamine gives you better sticky properties. It also is able to give you good dispersions in order to get us inkjet printed inks out of it. So our challenge was to use dopamine instead of polydopamine, and I can say that we have been able to successfully do that. That now we have a completely unpolymerized dopamine infused with PVA, and we, as you can see here, very sticky surfaces that we want to print, use as substrates for our material. The next step that she is doing now is she wants to create a sticky electronic surface for an application that we have. We have a funding for that. And now she's trying to convert this insulator. This is a complete insulating material. So this is the substrate. And now we are infusing electronic properties into it to make it conducting. So we are again now trying to play with the polymer chain here so that we are changing its electronic properties so that we can convert or get a transition from an insulator to a conducting material. So we can, the vision here is to have a same material substrate and the same material chain, electronic material printed on top of it. Because then you don't have an interface issues that you face with multi-material printing. If you have two different materials, you will face a lot of interfacial problems when you want to print on them. But if they all belong to the same polymer chain, that makes your life very much easier. And that's the vision of this. So we have been doing a lot of material studies, right? So now the thing is, where do this all take us? So there's has to have, as I said, I'm an engineer, I like to see things moving, not just make good materials and make them sit in the lab. So we have been using a lot of these applications in some real life scenarios. One of the application is what we started was 3 years back was when I was a postdoc in Singapore, I had this curiosity that, same thing. Can I print on different surfaces or not? Can I do this? So I started a very fun project. It was not funded, just out of curiosity, printing on textiles. Now we have different kind of textiles that you can woven, non-woven, wool, silk, whatever. And I started picking one of these every week, picking one of these materials and started printing on them. The idea was just to see whether I can directly print electronics on them, right? But it came to my notice that, of course, on some substrate, it was totally easy to print directly. In some, you needed some kind of pre-processing and post-processing. But when I compared some of these printing, the conductivity of this, they were most really printed with silver inks. When I compared the printing of these materials on ITO and glass, I found that the conductivity of some of these materials went higher when I printed on these textiles. And I was really interested to see that why it happened, why on a glass, which is a standard, gave me low conductivity or high impedance compared to the other ones. And then it came to my understanding when we investigated again the substrate and the ink interactions is that the binding of certain nanoparticles or certain morphology is very good with textiles. So when you bind them, they basically, you have fibers. So these are all nothing but fibers here, right? And when you have a material printed on top, they basically go and flow and wrap the whole fiber around them. So you basically wrap the whole fiber with a conductive material, just put it this way, right? And then you get a very good continuous pathway for the electrons to flow. And that basically ends up giving you a better conductivity compared to a standard glass, for example. And that basically gave us an idea. So I was talking to a doctor, she's a professor, and she practices on muscle atrophy in Copenhagen Hospital. And the idea was basically when a person is admitted to ICU, the first thing that happens, of course, they are dealing with the issue that they are admitted for. But the first thing that happens within 1 week of their admission is they start to lose a lot of their muscle mass. And it happens because they're completely immobile, right? They're not moving their muscles. They lose their muscle. And the standard way of treating this problem is that the patient needs to recuperate in the hospitals. Then after they are discharged, they have to go to a specialist where they are put these, you have seen these big bulky electrodes that they put on their muscles, the thighs and the hands, and they stimulate using the electric field with all different frequencies. Now, this is a problem, especially if you have kids or if you have elderly, because it's a long drawn process. You have to visit the specialist, it takes a lot of time, and it's uncomfortable as well. So we wanted to design something that could be used within the ICU settings itself. So if the patient is lying, why can't I start the treatment right there? Why do I need to wait for the patient to be discharged, right? So the idea was then nobody likes to be sitting and be immobile with big bulky electrodes. So that was not an option. So what we did was we made a material which was completely biocompatible. It was a good conductor, so it had low impedance. And then we printed on healthcare stockings. So these are the compression stockings that all ICU patients normally have to wear, especially in Scandinavian countries, I would say, because they are warm and they keep the muscles compressed, right? And once you print them, then you see that what we did was simply connected these wires to a very small stimulator, which is also made by us. And then the patients can then stimulate themselves at different frequencies while they are admitted in the hospital. So from day one that they are admitted, they just stimulate themselves for 30 minutes, the next day 30 minutes, so and so forth. And what we found that was a huge improvement in their muscle mass, muscle wastage. So we found that their muscle, so we have now 2 studies done, preclinical trials, clinical trials in COVID patients, and now we are doing bed rest studies in Copenhagen Hospital. And all of them have shown that from day 1 till day 7, within 7 days, you can save up to 10% of the muscle wastage just by using this. So this is what I'm trying to say is a fantastic example where you are incorporating and directly writing electronics on a piece of textile. That's nothing. There's no rocket science here. of course, the beauty comes from the material because it's a completely biocompatible material. It has a good low impedance to provide the kind of stimulation. And then you connect it with wires and then to a stimulator and you have a treatment. Basically, this is a treatment. Of course, now we are into the second generation of these stockings where we have now printed these wires so the patients can be completely mobile while walking around if they have to. So they don't have to be, ridden to the bed. So this basically project has taken quite a bit of wings. So we have done our COVID trials and now we are doing the bed rest studies and now we have further funding to take it further into a real setting, into the hospitals. So as I said, the idea is not just looking at or just printing. I mean, anybody can do the print, you give them ink and of course after certain optimization. But what I am really interested is to understand how the interaction of these things go with the substrate. In this case, it is a textile. So we are trying to do a lot of electroimpedance studies to understand that how our material that we have developed compares with the commercial pads that are available in the market. How is their interaction with the skin? Because we have done trials for 7 days to up to 10 days, and there was no complaint by the patients. So there's no skin rashes, there's no discomfort, no problem. So we want to understand what is going on, especially when the current goes from these to the muscles. How is the skin reacting and what is happening? So we are doing a lot of studies at that interface as well. This is another fun project, which again was a prototyping, where I said that my idea is to basically combine biology with electronics. The idea was, again, it comes from the fact that we want a lot of innovation when it comes to wound management. So if you look at the area of wound management right now as well, it's been the way the wounds are treated are very rudimentary. So if you have to inspect a wound, you still have to open the bandage and the doctor has to, or the healthcare person has to inspect those wounds, right? We are so technologically advanced, it just makes me wonder, why can't we have sensors around the wound area on the bandages? Why we don't have them that can give us an indication of the wound, how the wound is doing? When a wound is healing, there are a lot of changes that happen, especially the physical changes. There are a lot of chemical changes happening, of course, but there's pH changing in the wound or around the wound area in your skin. There's oxygen level changing. There's temperature change happening. And if you monitor these changes, you can actually monitor which way your wound is going, whether it's really going to heal or not going to heal, or it's going to cause a problem. And the idea was to create these wound patches. Now, wound is a very, very sensitive area. And you cannot put hardcore electronics, those wires around the wound area. No. So what we wanted to use was hydrogels. Hydrogels are the most successful tissue engineering materials, which have already proven their competency in that area. And we wanted to, so what we did was we 3D printed that material as a patch. And then we wanted to infuse electronics into, well, this is not really an electronics, but kind of an electronic material into that. So we can have some kind of heating element and some kind of interdigitated electrode. Why these two elements? Because there's some consensus in the medical community which says that if you have some kind of heating and some kind of electric stimulation at the wound site, then your wounds tend to heal faster or slightly faster than a normal chemical treatment. So we wanted to make that patch with some kind of heater and some kind of electro stimulation. And we did that. So what we did was, this is an in-house made silver ink. It does not require any heat treatment or any post-treatment. So the moment you print it, it's good to go. So that's why it's completely compatible with such a low temperature underlying material. So it's silver nanoparticles on hydrogel, sandwiched between two hydrogel layers. So there's hydrogel, silver ink, and then hydrogel. And that's simply a patch. And of course, yeah, we all have the problem of interconnect, so we still need to connect it with wires and so on and so forth. And then we see. But what we saw was that basically this kind of a platform is completely compatible with the human body or around the wound area, because you do with, I mean, the biggest concern for the doctors or the health professional is, what if your silver ink leaks, out of this and it goes into the wound? Or would it kill the cell? So we basically did prototyping where we did cytotoxicity tests using CT12 and human skin cells. where we say that the inks that we have developed are completely biocompatible. They do not kill the human cells. I don't know for sure how good or bad it would be for the wound. Of course, you don't want silver to be leaking in your wounds, that's for sure. But at least it's not bad for the skin that where you put it on, right? So that's the whole point. So baby steps. The other project that we are running is on biodegradable materials, as I said. So again, it all comes from the need from the medical community. So when you have an implant being done in the human body, once your body is closed, the operation is done, the implant is implanted, there's no way for the doctors to know how well the implant is being accepted by your body. There's only 50% chance, by the way, for the implant to work successfully. There are 50% chance that the implant will be rejected by your body. And then another operation has to be done, to replace that implant. There's a growing need in the community to say that, what if I can put some sensors with the implants and have some antennas going in with the implants, which can detect whatever is going inside. I don't know to what sensitivity levels, but something, an indication. And then once that implant is accepted, you don't need that electronics there, right? You don't want to do another operation to remove that electronics. So that electronics should be completely bioresorbable. So the idea here was to print antenna design on what we have a tissue engineering material. It's a completely bioresorbable material. It takes about 1.5 to 2 months in human body to completely resolve, and then and leave nothing behind. Now, a lot of you would say, oh, it's very simple. You have the ink, you have the substrate, go ahead and print. Life is not easy for electronics engineer, let me tell you that. If you have to print an antenna design, the first thing that I need to know is the properties of my materials most of the time. This is a tissue engineering material, and that's the biggest challenge in my line of work. The materials I deal with are biomaterials. The electronic properties have never been investigated. So that becomes our first challenge. First, we need to investigate the electronic properties. We need to design the circuits according to those properties, and then we need to print them. Okay, so it becomes, and the printing for, especially for this is a PLC's biocompatible material. It's basically a fiber. If you tear this apart, it's completely stretchable, but it will come out in terms of very thin fibers. And printing on fibrous material is not easy, but we had the knowledge from printing on textiles. So we use that to print directly onto this and into this material. So what we did was, it's again, proof of concept study. We printed on this PLC material, an antenna design which works very well. And if you put this into the environment of a human body that is at 37 degrees with the right temperature, right oxygen level and CO2, it completely takes 2 months to reprint and it leaves nothing behind. So that's the whole idea of going forward. Again, for the wound management, what we did was basically here printed a device. Basically, it's on PDMS based, and then we printed carbon nanotubes and silver. And then the idea was to look into the chronic wounds here and only concentrate on the pH of the chronic wounds. So we made the material so that they can only pick up the signals in the chronic wound pH and try to detect the pH change. Now, you have to be mindful because when we say for wound management, these things, again, because they use some kind of electronics and they have silver and carbon, which is not very well, let's say, considered safe by the biomedical community. They cannot be put on the wound site. Nothing can be put on the wound site. They can be put near the wound site. So it has to be on skin application near the wound site, but not on the wound site. So we have to be mindful of that. But yeah, so this is kind of the patches we are making different kind of patches like this for temperature, oxygen, for pH, so and so forth, for different applications. Another one of the example which Eric also talked about in his talk was that this mesh of wires, that you deal with. And I've done work in Singapore where we basically printed wires for drone company, because in the drone you have so many mesh of wires, and they were so frustrated. Same goes for these biomedical devices as well. Most of these biomedical devices are so tiny, right? They're so tiny, and then they have a mesh of wires into them. The idea was that if we can miniaturize electronics, but we cannot miniaturize these wires. I still need to find volume and space for these wires to be fitted somewhere. And he's my colleague, Pribin. He basically is an expert in EEG devices where he's trying to pick up the signal, EEG signals from the ear. So it's for sleep monitoring and so forth. And one day he came to me and he said, Shweta, can we do something about these wires? Because he has this small device which can be fitted into his ear, into any ear. But he has these like 15 different wires that he needs to find places to put them. And then he said, what we can do. And mind you that in electronics, especially when it comes to printed electronics, we have seen so many scenarios where we have printed interconnects. We have printed, interconnects, and we can totally do that fantastically, stretchable form, whatever form. But we have not looked into cables. In electronics, we use 100 different kind of cables with different frequencies, different powers, high power, low frequency, high frequency. And again, if the idea is to replace a complete chip, then we would need these cables to be replaced, right? So this, what we basically, I took up as a proof of concept study was to look into this coaxial cable. So we use a lot of coaxial cables. And idea was to change its form factor and then see if we can basically get the same kind of performance in this by printed electronics. So again, it's a different form factor because it's a different technology, which is good and bad in both ways, if you can argue. But the idea was to basically use a multi-layered structure where you have an insulator, you have a signal layer, then you have another insulator, and then you have a shield. And then basically you are able to print them in small, so we can really print them in small 2 cm by 2 cm space. And then you can print different kind at different frequencies and make them shielding, get the shielding. Of course, the shielding, I would say, is not as effective as you would get with a normal shielded cable for low frequencies, but it works fine, especially if you're working with low frequencies. So we are able to show that application for low frequencies, and that works well. So that's basically the gist of my work and my talk. So I hope I have given you, a flavor of what printed electronics is, how it looks like, the landscape of printed electronics, especially the drop-on-demand technologies. And then I have taken you into some of the research that we are doing at Aarhus University, where the idea is to basically reshape electronics, as I said, where we want to make it more biocompatible, we want to make it more biodegradable, more greener in that sense, but also need to find where printed electronics can really serve. And for me, at least for our group, we found that niche belongs into the healthcare and the biomedical sector, because electronics has so much to give to that sector, and we have been doing it, but we need to change our thinking and the way in which we are delivering in some ways, and that's what we are trying to do in our own research. So I would just want to say a thank you to all the collaborators that I work with, and of course all the funding agencies. And yeah, just like Eric, I have some so we have this Journal of Material Science and Additive Manufacturing. So it's all about materials that we use, metal, polymers, electronic, biomaterials. So please feel free, it's a new journal, to contribute into this journal, and we hope to see your publication there. So that's all from me.